In this video, I'm going to talk about resonant frequency. So the resonant frequency, the most important points are resonant frequency will occur uh, only if there is inductor and capacitor in the circuit. There must be at least one inductor or one capacitor must be. Okay, so if there is only RL circuit, impossible to have a resonant frequency. So no resonant frequency. Usually resonant frequency we indicate with F0. Okay, so no resonant frequency. If you have RC circuit, no resonance frequency. Okay, so in that circuit there must be L and C components to have a resonant frequency. Now the second point is it tells us how fast an energy is moving from one component to the other component. So how fast energy is moving from inductor to capacitor, capacitor to the inductor. So for example, you have a source free inductor and capacitor. Assume that there are no losses. Okay, and assume that this inductor is fully charged. What happens when we connect this? The current is going to go around this. Okay, so the capacitor will discharge and inductor will charge. At the same time, I'm assuming there is no resistance, pure inductor and pure capacitor, so that there are no power losses. Okay, so again, once it is fully charged, what happens? The energy will transfer back to the capacitor again, so that cycle will continue. So for the positive half cycle, so if you look at the whole cycle, okay, so for the positive half cycle, from here to here, the current, say this is the current I of t, okay, and here is I of t. Okay, so for the positive half cycle, up to this point the current is reached the maximum value. So what happens there? This capacitor is discharging and inductor will start charging. Once we reach the maximum value, by the time the energy stored in the capacitor is going to be 0 and energy stored in the inductor is going to be maximum. Now from here to here, from 90 degrees to 180 degrees, inductor is fully charged, capacitor is empty. So what happens there? The capacitor will start charging and inductor will start discharging. So still the current is going to go in the same direction because inductor does not allow sudden change in current. But now this inductor, this will have positive charge right here, negative charge right there. Okay, so once we reach by 180 degrees, the inductor is fully charged, but the bottom plate is going to be positive, top plate is going to be negative. Okay, once it is fully charged, again, now the current will start flowing in the opposite direction. So that's the reason we see the opposite direction. So again, inductor is going to be fully charged by now and capacitor is going to be empty. Once it reaches there, again it will come back to the original state. That's called complete cycle. Okay, so it tells us that how fast that energy is moving in the LC circuit. So that F0 for the LC circuit is 1 over 2 pi square root of LC. Okay, I'm not going to derive this for LC circuit anyway. This is from your physics class. We're going to talk about resonant frequency, how to find the resonant frequency for RLC series circuit, parallel circuit, and series parallel combined circuits. Now, at resonant frequency, so that's what the resonant frequency is. Resonant frequency is nothing but it tells us how fast energy is moving from one element to another, one energy storage element to the another energy storage element. Okay, and there must be L and C in the circuit, then only there will be resonant frequency. Now another important point, we're going to use this a lot. At resonant frequency, imaginary component equal to 0. Okay, so there is always the imaginary part of that circuit is always 0 at resonant frequency. So based on this, we're going to use this a lot. We'll find the resonant frequency. At resonant frequency, Z equal to R. Okay, so total imaginary part is going to be 0, so total impedance equal to the resistance. Since impedance value is decreased to only resistance, now at resonant frequency you will see highest current passing through the circuit. Now we'll do a simple RLC circuit. So here is a RLC circuit, R, L and C. Okay, this is connected to a AC source with voltage and frequency, R, L, C. When I convert this into our frequency domain, this is j omega L, this is minus or 1 over j omega c. Okay, or you can take the j numerator, it's going to be minus j over omega c. But whenever we are finding resonant frequency, do not separate j omega. So keep j and omega together all the time. Do not separate them. So what I'm saying, do not write minus j over omega c. What happens if I write it? Yeah, nothing happened. Your calculations are going to be a little difficult when you're solving the examples. So I'm going to keep the j omega together. Okay, so mathematically you can write it, but your calculations are going to be a little bit complicated. So to avoid that complication, I will keep the j omega together. So here what is total impedance? Total impedance equal to R plus j omega L minus 1 over j plus j 1 over j omega c. That's my total impedance. Now to find out the resonant frequency, I need to make the imaginary part equal to 0. So I need to make j omega L plus 1 over j omega c equal to 0. When I make the imaginary part equal to 0, okay, so j omega L minus 1 over minus j over omega c equal to 0. So omega L. One important point, whenever I say imaginary part equal to 0, so I'm saying imaginary part equal to 0. Okay, whenever we say imaginary part equal to 0, now it's no longer called as omega, we call this as omega naught. Okay, because it's at resonant frequency. Omega naught is angular frequency, so we're finding angular frequency. From there you can find the resonant frequency. We know that omega is nothing but 2 pi f, okay, or omega naught equal to 2 pi f naught. So the resonant frequency we are always indicate with f naught. So here omega naught L equal to 1 over omega naught c. Okay, omega naught square equal to 1 over LC. So omega naught equal to 1 over square root of LC. This is what the resonant angular frequency. When it comes to the f naught, 1 over 2 pi square root of LC. So this is the resonant frequency for RLC series circuit. Remember, this is for only this circuit. Okay, this is not valid for any other circuit. Okay, now I'm going to find the resonant frequency for RLC parallel circuit. So here is my R, L and C. Okay, RLC parallel circuit. Now the impedance equal to 1 over Z total equal to 1 over R plus, I'm going to convert this into frequency domain. So this is j omega L, this is 1 over j omega C. So here 1 over R plus 1 over j omega L plus 1 over j omega C. Okay. So when we do the parallel circuit, usually instead of doing impedance, we will do with admittance. So this 1 over Z indicate with Y, we call this as admittance. Okay. The units for admittance used to be mho, and sometimes it's just reverse of ohm, mho, but these units are no longer used. The real unit is Simon. The unit was changed in 2004 2005 recent years. Okay, so they used to have the Simon in the previous years too, but most of the time we used to have mho or mho symbol, but they no longer accepted. Admittance is measured in Simon. Okay, and 1 over R we indicate with G called conductance. Okay, and 1 over X is called B, called susceptance. Okay, susceptance. So Y equal to G plus or minus J B. Okay, so here I can write 1 over Z equal to Y, 1 over R equal to Z, plus, okay, so this is 1 over omega L is nothing but, so omega L equal to BL, and 1 over omega L equal to BL, so it's nothing but minus J BL. This is going to be plus J BC. Okay, so we'll have imaginary part and real part. So now I'm going to make this imaginary part equal to 0. So when I make the imaginary part equal to 0, so minus, so this is J minus J over omega L. This is plus J omega C equal to 0. So if we make it equal, 1 over omega L equal to J omega C. When we make the imaginary part 0, make sure you put it as omega naught, and at the same time you can ignore the J term. I'm just writing the J term here to make sure, we're copying only the imaginary part. Okay, so 1 over omega naught L equal to omega naught C. So omega naught equal to 1 over square root of LC. We had the same formula for series circuit. Luckily, we end up with the same formula for parallel circuit. But in the exams, I saw so many times students were using these two formulas to find resonant frequency, to find a resonant frequency for a circuit. Never ever use these formulas to find resonant frequency for other circuit. This is valid only for the RLC parallel circuit, and the previous one, luckily it's the same thing, is valid for only RLC series circuit. Okay, I'm going to stop this video here. In the next video, I'm going to find resonant frequency for a series parallel combination circuit.